Greetings and welcome, friends. You've made it. You have entered into a new zone, this awesome blue zone, where we're learning about quadratic functions and inequalities. So this is our first day checking it out. Just to recall, quadratic is referring to squared, right, terms, right, squared degree things. Functions, you might remember linear functions, equations of lines, stuff like that. And inequalities, of course, you guys know that as being like these guys, right? That was a sad, there's a better one, right? And today, the section that we're learning is solving quadratic equations by graphing. So the first thing I want to talk about is quadratic functions. All right. So we've seen quadratic equations before. Quadratic functions, however, a function is going to have multiple variables represented. So it would be something like this: y equals ax squared plus bx plus c. Would be a quadratic function. It's quadratic because the highest degree is 2, hence quadratic. Whoa! And it's a function because it's a relationship between y and x. All right. By the way, sometimes y, which maybe this is the first time you've seen this notation, instead of y, we might write this as f of x equals ax squared plus bx plus c. And that means the same thing. F is just the name of the function. F of x is how that would be read out loud. So it's not f times x, that's f of x. And what that means is, what is the value of the function f when you input something for x? All right, that's kind of what that's referring to. So if I wanted f of 1, well, f of 1 in this case would be when I plug in 1 for all my x's, and whatever number I get is the corresponding y value, or f of 1. All right, so, but we'll get plenty of practice with that. So quadratic functions are going to look like that. Graphically speaking, let me draw a nice little picture over here. Yep. Graphically, we're going to have pictures that, there we go. Something that looks like this. And you might know what this is called. Does anyone know what kind of graph this is? It's a parabola. Right? So a parabola it's not a U shape, but it does have a smooth transition here. It's not a V shape because it doesn't come to a point. The reason it's not a U shape is because it's actually getting steeper and steeper, faster and faster, whereas the letter U eventually gets vertical. All right, this never gets vertical, but it does get steeper and steeper. So that means I could actually plug in really big x values, and I'd get really, really big y values in this case. So, significant stuff about a parabola. And I think you've seen some of this before, but that is good. That means it will be review. So let's see. The most significant thing about the parabola is this point right here, where it changes direction. All right? Does anyone know the name of that point? Yeah, it's called the vertex. Yep. So vertex is what that is called. I've actually heard some books literally refer to it as the turning point, but I shy away from less common vocabulary, even if it's more friendly, only because it's not universal, right? So then when students who learned this as the turning point, when they took a standardized test or talked to any other mathematician, they were like, what are you talking about? What do you mean the turning point? Or they were confused about what's the vertex, right? So that's why I try to use the exact language.
Would they actually get it wrong on the test?
Well, if it asked those students what was the vertex, they wouldn't even know what it was asking, right? So it would depend. I don't know how as far as the other way around. But what would you call these points here? Yeah, those guys look like xintercepts. And notice that was plural. What? There's multiple x-intercepts. Craziness. All right. And another significant point, but not as important in the world of parabolas, is this point here. It looks like the y-intercept. The yintercept. And yeah, it's related to the quadratic formula. That'll be coming back at one point in this chapter. And I can sing it, that's right. Check out that video, subscribe. Now, one of the things I want to point out about x-intercepts and parabolas is there's two of them, or can be two of them. There's not guaranteed to. Question, is it possible to have a parabola hit the x-axis at one point? What would that look like? Yeah, the vertex would like do something like this, where it ricochets, right? It just hits the x-axis once and just bounces right off of it, right? It just gives it one little peck on the cheek and then runs away. Is it possible to have no x-intercepts? Yeah, something like this, where it's just like never even went close to it. And also it's possible, by the way, to have upside down parabolas, where this guy would never cross it either. So parabolas have as many as two x-intercepts, but they don't have to. Okay. So let's see. Another feature that parabolas have is what's called an axis of symmetry, where if you draw a vertical line through our vertex, that line is a line that mirrors the entire parabola. All right, so this point is mirrored. It'd be the same distance over here. It would land there. Okay? This is called the axis of symmetry. Line of symmetry also would describe that concept in general. So, axis of symmetry is that. I think there is. Yeah, think about the m's being mirrored. But anyways, so that's kind of a bunch of facts about parabolas. But now our question is, how can I get from this to this? Right? What information can I pull from a function, right? An algebraic representation of it, and then suddenly get a graph out of it. And you might remember back in the days of y equals mx plus b, you might recall that when you looked at that equation, right, you'd be able to find the slope, you'd be able to find the y-intercept, and be able to pull valuable information out of its function. In the case of parabolas, we will use the information from our function. All right, we will use this a, this b, and this c, but none of them necessarily super quick represent, oh, that's what the vertex is. I actually can't tell without doing a little bit of math first. Or I can't just look at it and be like, aha, that's the x-intercept. A is the x-intercept. Nope, it's not the case. One of those will actually quickly translate for us, but we'll get to that in a minute. So, all right, so here's the idea. Let's find ways to take information from my function and get all of this valuable information. So the first thing let's talk about is the vertex. How to find the vertex. You got it. So the vertex we're going to refer to as the point h comma k. All right, that's so h would be the x coordinate of the vertex, k is the y coordinate of the vertex, coordinate. Am I right? So if I want to find the x coordinate of the vertex, there's actually a formula for us. H is going to equal negative b over 2a. And that will always give us the x coordinate of the vertex. Actually, maybe I'll even label my vertex as h comma k on my picture. Yeah, that 2 does look like a z, but just pretend. What was the question? That's true, yeah. When I write a z, I try to draw a line through it for sake of distinguishing it.
I think you made me write my sentence like that.
Aha, excellent.
Yeah, I write my sentence like that.
Now, k, the y-coordinate of the vertex, well, check this out. Let's say I knew what the x-coordinate was. Let's say the x-coordinate was like 2 or something. So if this was 2, how could I find its corresponding y-coordinate? What would you do if I told you that was 2? Well, I would have an equation. So what you'd actually be able to do is plug it in for x, and you'd get the corresponding f of x or y, right? That's the same thing. So you could find y by plugging this in for x. So let me show you a formulaic way of thinking of that. That means k, the y-coordinate of my vertex, is just going to be f of h, which just means plug h into the function for x. Or, if you want to write it out a little bit more explicitly, that would look like this. H squared plus bh plus c, where I've just taken x and replaced it with h. But the actual process, or the little formula, I guess, if you want to think about it, is you just, k is equal to f of h. And that will find the vertex for us. Hooray! Vertex. Next thing we'd find is the x-intercepts.
This is fun.
I'm unsure if that's sarcastic or not.
No, it
I don't-
actually is.
Excellent.
Because you
Good.
write like a bunch of stuff and you look so smart, but it's just like a pattern that you do.
Oh, sure. I love it. Great. So guys, for the x-intercept, my little orange tick marks here, what could you tell me about the y-coordinate of those x-intercepts?
What can you tell us?
Well, I want you to think about it.
I shift a little bit less.
Or in fact, any point on this x-axis, I think I heard someone say it, what would the y-coordinate be?
0.
0, right? So this point would be like 10, 0 or something like that, right? All of the points on the x-axis have to have a y-coordinate of 0, otherwise they're not on the x-axis because I would have moved up that y amount or down that y amount. So I'm going to use that fact that the y-coordinates of my x-intercepts are 0. So to find the x-intercepts, this is what I'll do. I'll say, let's set f of x, my y value, equal to 0. What does that look like? That would look like this. ax squared plus bx plus c equals 0. So I'd set it equal to 0, and then I'd solve. All right? And in order to solve, I'd actually have 3 ways I could do that. One of them, if I've got a quadratic set equal to 0, I might factor. Second way you have not heard of yet, but we will by the end of the week, I think, is complete the square. And the third way you have heard of, and already mentioned it, is the quadratic formula. Yeah, so factoring only works some of the time. The other techniques work all of the time. But factoring, I think, most of the time people think is easier. So use whatever works. So if I had ax squared plus bx plus c equals 0, and I was solving my factoring, I would end up, getting this times this equals 0, right? And I'd get it factored, and then I would set each factor equal to 0. And then I'd end up getting x equals something and x equals something. All right? And those values are going to be our x-intercepts. Right? Right, DJ? So, the x-intercept, sometimes later on in the course, we'll refer to my x-intercepts as S1 and S2, which is kind of weird. So, those would actually end up being the ordered pairs S1, 0 and S2, 0. We'll do a for real problem out in a moment. I just want to kind of walk you through the whole process here in general. So that's how I could find the x-intercepts. The y-intercepts, everyone's going to love. It's going to be great. Everybody.
Yeah, that's disgusting.
Y-intercepts, here we go. Now, question. What could you tell me about the x-coordinate
0.
of the y-intercept? 0. Because if it wasn't 0, then that means I would have moved to the right or to the left of that point, and it wouldn't be on the y-axis anymore. So, I'm going to use that concept. Actually, I'll show it from up here. I'll use that concept in order to find the y-intercept. Now watch this. This is even better news. If I was to plug in 0 for these x's, I would have had 0 here and 0 here, right? What is 0 squared?
0.
Times a is
0.
0, and b times 0 is 0. 0 plus 0 is 0. So f of x, or f of 0, is just going to equal c. So it turns out my constant is your y-intercept. Just like y equals mx plus b, b was the constant in that case, and it was your y-intercept. The same thing happens for quadratics, and in fact will happen for any function. Your constant will always be your y-intercept. Cool beans. So
C equals y.
so the y-intercept is c, or you could think about that as 0, c if you want to think about it as an ordered pair. All right? So that's the easy one to find that we should be able to figure out just by looking at the equation as long as it's written in the correct form. Let's see. All right. Now a couple other things about parabolas. Well, let's actually talk about axis of symmetry. Now for the axis of symmetry, it's the equation of a vertical line that passes through my vertex. Now the equation of a vertical line is always x equals a number. All right? So it has no slope or an undefined slope because it's vertical, and it's x equals a number, and the number that it equals is the wherever it crosses on the x-axis, which is the same place it crosses through the vertex, which is h in this case. So my axis of symmetry is, more specifically, the equation x equals h. Now if you told me just h is a number, but x equals h is an equation that represents a vertical line. All right, so I just want to point out that it's this entire expression, or equation rather, that's needed in order to describe the axis of symmetry. All right, a couple other things. Which way does the parabola open? Okay. So by, I don't know, apparently I do. Now what I mean by open is which way is the parabola opening up towards, or where do its end points kind of point towards, the arrows? I guess those aren't points. Points up in this case. Now it turns out the direction that this opens is directly related to our quadratic term, which is the most influential for larger values of x. And the x squared part is not going to determine the positivity or negativity of this, because even if I plug in a large negative number, squaring it makes it positive. So the only thing that would make this negative would be the a. And if it was negative, it would be opening down. And if it's positive, it would be opening up. So it turns out a can be used to determine the opening. So if a is positive, it opens up. All right? And you can think about that as like it's smiling. It's positive, right? Oh, look at that little smiley face with some dimples. Yep. And if a is less than 0, it opens down. So if you have a negative leading coefficient, it's like, meh, sad face. A sad dabbler. All right? And now there's another thing, craziness. that we could analyze about this is it the shape of the parabola? Okay? Which a regularly shaped parabola has some really unique features that I'll talk about. Maybe I'll talk about it in a minute. So a regularly shaped parabola looks kind of like this, but I also could have kind of like a tall and skinny parabola, or I could have a really like wide parabola. And to figure out the shape, it's actually also related to A. If the absolute value of A is greater than 1, and we'll describe what I mean by that in a minute, then it turns out it's a vertical stretch. No, S-T-R-E-T-C-H. All right. And if the absolute value of A is less than 1, then it's a smoosh, vertically speaking.
Seriously?
That's my own word, but sure. So let's see. If this is a regularly shaped parabola in this case, what do I mean by a stretch? A stretch, imagine like stretching a piece of gum vertically, it's going to get skinnier. Right? So a stretch would look like that compared to the regular shape. And a smoosh, I'm smashing some Play-Doh or silly putty into a table, and it's going to make it spread out and get
I feel
wider.
like it should be the opposite.
Well, this is vertical stretch, is how I'm describing it. I technically could view this as a horizontal smoosh, if you wanted to think about it that way. Or I could view this as a horizontal stretch, which is a fine description as well. And I'll even write that one down.
You're just gonna confuse us.
Well, I'm trying not to, but
It happens.
it happens. So, what do I mean by absolute value of A is greater than 1? Well, let's consider some examples. So that means A could be things like 2.
4.
Would -4 work?
No. Wait, yes.
Yeah, because the absolute value would make it positive. Would 3/2 work?
Yeah.
Yep, because that's bigger than 2/2, which is 1. All right, so what's an example that would work in this case? 1/2. Okay. How about -3/4? 6/7.
So pretty much fractions.
Well, here's a fraction, but any fraction that's between -1 and +1 is how I describe these, where these fractions, their magnitude is bigger than 1, or their absolute value is bigger than 1. All right, so just so you're aware of that. Now, this is a super not technical way to think about parabolas, but I can think about the slopes of a parabola, which is in quotes because technically when you take calculus, you'll find out that the slope of this parabola is constantly changing, and you could actually find the slope of like a tangent line, where the line that hits it at exactly one point. But I'm referring to slopes in kind of a much more broader sense, where the slopes of the parabola, it turns out that a regularly shaped parabola, if I have the vertex, if I go up 1 over 1, that would land me at a point. I could go up 3 over 1, and that would land me on a point. I could then go up 5 over 1, and that would land me on a point. Does anyone see what they think might be a pattern between the rises? It's going up by 2. What's another way you could describe those numbers?
It's like rise over run.
Yeah, it's rise over run. But what about these numbers, the 1, 3, 5?
Odds.
They're odd numbers. So it turns out the slopes of a parabola are consecutive, or the rises maybe I could say. Rises are consecutive odd numbers.
And it's not like a
What, consecutive?
yeah.
Consecutive. I like it. I like it. All right. So up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1, up 9 over 1, up 11 over 1.
Why can't go up an even number?
Well, it could if you change the value of a. So the actual slopes, you could think about it this way. So let's say whatever a is, if a did a stretch, for instance, it would change these rises. Let's say a was 2. Let's say if a is equal to 2, hypothetically, then my slopes would be 2 times 1 over 1, 2 times 3 over 1, and 2 times 5 over 1, which I could simplify those to be 2 over 1, 6 over 1, and 10 over 1. So if you do have a stretch, the value of a can actually change what your quote-unquote slopes are. And then that would land you some extra points that you could actually figure out the shape of this parabola a little bit easier. And then you could mirror them on the other side as well if you wanted. So, okay. Whew. There's a lot of facts about parabolas. Let me do an example for real now. Exemple. And we're going to have like an example today, literally. But that's quite all right.
Cool.
So let's see. Let's graph and find all significant points of the function f of x equals x squared minus 12x plus 24. So, all right. First thing I want to find out is this in the ax squared plus bx plus c form? Yes, because I've got x squared, my linear, then my constant. I'm good. And I don't have it like something besides y or f of x over there. So what are the values of a, b, and c, since those are going to be used so much? What's a equal to here? 1, right? That's the leading coefficient. What's b equal to? Negative 12. It does actually include the sign, but it doesn't include the variables, right? I do have people that think negative 12x is b. That'd be my b term, but not the value of b. Okay? And what's the value of c? 24. And that also includes the sign there. So there's a, b, and c. So let's actually start finding stuff. Here we go. Let's get the vertex. Vertex is going to be negative b over 2a for h. So negative of negative 12 over 2 times 1, right? So that's 12 over 2, which is 6. So there's the x-coordinate of my vertex, the h. Right? So I just follow this little formula. To find k, what did it tell me to do? Find out what f of h is. So what is f of 6? So that means I'm going to plug in 6 for all these x's. So that's 6 squared minus 12 times 6 plus 24. 6 squared is 36 minus 72 plus 24. So that's 36 and negative 72, I believe, are negative 36. And I'm going to get k equals, what's that? Negative, wait a minute. Yeah, negative 12. All right. Did I do that right? Yeah.
How come it's from the negative 30? It's 36 minus 72 negative 36.
Yeah.
Ain't that a fun?
And actually, a lot of times, the first two terms happen to be, like the first term happens to be half of the second term, weirdly enough. Excluding kind of the sign stuff of it, but so there's the value of k. So that means my vertex is the point what?
6 and negative 12.
6, negative 12, right? If I want to write that as an ordered pair, which sometimes can be helpful. Did we do that right? Yeah. Okie dokie. So, let's see. Now we want to find what? The x-intercepts.
Which we should hopefully do in quadratic form.
We could.
Okay, fine.
So I can sing.
Well, I'm going to have a whole lesson on the quadratic formula next week.
But Mr. Wadi, I want you
Wait,
to
yeah, we
sing.
should factor just because of the numbers work out well.
Yeah, I think I chose a problem where the numbers might work out well for us. So to find the x-intercepts, they said you set it equal to 0, right? I replace y with 0, or f of x is replaced with 0. So to solve this, I think I chose one that's factorable. Can I GCF anything? No. Is it a pattern? No, that's not a perfect square. Do I have to AC method it? No, because that's a positive 1. So let's just find the factors of 24 that add to be 12. Any of them work? No. Wait, right? No, they don't work. That's a shame. That's two things that won't work. So let's quad formula it then. Looks like you got what you wished for. So the quadratic formula, I'm going to do a whole lesson on this later, but here's the formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. There we go. So I already know a, b, and c because it's the same a, b, and c that I had earlier. So I'll do x equals negative b, or opposite of b, is positive 12 plus or minus the square root of negative 12 in parentheses squared minus 4 times 1 times 24 all over 2 times a, 2 times 1. So x equals 12 plus or minus the square root of negative 12 squared is positive 144 because it was in parentheses. Let's see, 40 plus 12, was this 92? Is this right? No. 90, yeah, 4 times 4 is 16. Thank you, friends. Got my back. So x equals 12 plus or minus the square root of, what's that, 48? You know, it's a shame that that's not 49. Square root of 48, I think 16 goes into it, so I could partially reduce that. But I'm actually interested kind of in the decimal variations of this. So I'm going to do 12 plus the square root of 48. Is, let's see, 18.928 over 2, and 12 minus the square root of 48 is 5.072 over 2. And then I'll divide those and I'll get x. And also notice that my sign went from very confident in itself and now it's kind of nervous. It's like shaking. It's like, is it? Yeah, it's like unsure of itself. 18.928 divided by 2 is 9.464. Or 5.072 divided by 2 is 2.536.
That squiggly looks like another X.
What area code?
Oh, it almost does there, yeah. So I call those squeakle signs because they're squiggly equals. And now what I want to point out is sometimes, this is what students do, so I'm just going to write no and show you what they do wrong. They'll write 9.464, comma, 2.536. Super no. In fact,
Because it's not 1 point, it's 2 points.
right, those are two separate points, and what are their y coordinates?
0.
0, okay? So I just want to point that out. I'm going to call that 9.50 roughly and 2.50. Okay, so it might be helpful for you to write that as two separate points so you don't accidentally make that mistake. So that's my x-intercepts. Let's see, y-intercepts. Yintercepts. That one's easy. What's the y-intercept?
And on one hand, or
24.
24, right? It's just the constant. So the y-intercept is 24, or 0, comma 24 is the point that it passes through. What else can we find? Axis. The axis of symmetry, the AOS, is going to be x equals the vertex. X coordinate, 6. Right? X equals h, so x equals 6. It's the axis of symmetry. Which way does this open? Because 1 is greater than 0, right? Because 1 was the value of a, so it opens up. And what about the shape of this? Yeah, a is the absolute value of a equals 1, so it's a regular shape, right? So there we go. So let's see if I can graph this.
like, so how many parabolas are in there?
Don't worry about it.
Okay, so
So let's see. Let's visualize what's going on. The vertex is at 6, negative 12, and it opens up, and it has to go at least as wide as those. So I'm going to have... so let's see. It goes down as far as negative 12 for us, and it opens up. I think something like this should do. So I'm just kind of visualizing where it goes. Let's see, what was the other? 9 is where it crossed, right? Yeah, so something like that.
Okay.
So I'll give you a chance to write this down if you can't keep up with the video after this. But you can at least start it. So let's figure out, okay, where's the vertex on this? 6,
0.
negative 12. So over 6, down 12 is right there, right? So there's my vertex. What other points do I know? 0, 24. Oh, that one's way off my chart. That's going to be like, it's going to be like here,
X equals 6.
right? Something like that, maybe.
Way to go.
So if I could have fit my scale a little better apparently. But let's see. I also know my x-intercepts are around 9.5 and 2.5. So I'm expecting around 9.5 and 2.5 to be where it crosses there.
Axis of symmetry.
That's so not too
No? Did I not count the scale?
9.5 is not 9.
Oh, you guys are so good. It's a good point. These tick marks clearly were not correct. Here's 9, so 9.5 is here. You're right. Thank you, friends. You got my back. And then 2,
That's 3.
3, bam, 2.5. I like it. Now, let's think about the shape of this graph. What are the slopes on this doing?
it's pretty steep.
It's a regular shape. So from here, I can do the up 1 over 1,
And then up 1 over 3.
and then up 3 over 1.
Right.
All right. And then up 5. 1, 2, let's see. 1, 2, 3, 4, 5 over 1, right? And then after that, it would go up 7 over 1, right? So 1, 3, 5. So those give me all new points that I can plot. Ba, 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 ba. And that's why this crossed at a funny spot, because it would have had to go up 3 over 1 to land exactly on the grid. And with the axis of symmetry, which someone mentioned a moment ago, which was x equals 6, I can actually mirror those points. Now check this out. This is 1 unit away this way, so therefore there must have been another point 1 unit away this way, right there. This is 2 units away that way, so then 2 units away this way, mirror. 3 units away, 3 units away, right there. So you guys see how I can mirror those using the axis, right? So that's a good trick. Those are like freebies right there. Yeah.
You know, Larry, maybe I have like something sarcastic. You shouldn't bring her down. You shouldn't bring her down.
And here's my parabola. So I would ask that you would try to have at least 5 points for your parabola if you could.
Honestly, I don't like drawing the lines. It's going to irritate me.
I'm sorry.
I don't have a ruler for it.
These lines, the orange ones?
No, green one.
Yeah, there's no ruler for that.
Exactly, that's why I don't.
That's why That's why what matters to me the most are the locations of your points, and then your curve, I understand, is going to be a rough sketch.
Alright, my brain is solved.
Now guys, check this out. You might have realized, if you were particularly keen, you might have noticed, wait a minute, we were talking about solving quadratic equations by graphing. All we did was quadratic functions, and we graphed them.
Oh my god.
I didn't even talk to you about what we were supposed to. Now, behold, we're going to back into this right here.
Okay, this is getting way
No, don't worry. Don't worry.
Way too long to a video.
You're fine. You're fine.
Thought you said the idea
So,
of one set both.
If I wanted to solve by graphing, this is the trick. I'm not going to do a whole problem. Stop complaining and just follow along. Here we go. If I wanted to solve by graphing and I had x squared minus 4x plus 4 equals 0, this is what you would do. All right? As long as it's set equal to 0, you would replace 0 with y. Witty with y. Withy. Okay? So replace 0 with y, or f of x, and that would give me a y equals 2, and I'd have a quadratic function. You are going to graph that function, and it turns out that since I said y, right, I replaced 0 with y, that the values on the graph when y is 0, those would actually be the x values that would answer this equation. So what y values are 0 on the graph of a parabola? The x-intercepts. So it turns out that if I wanted to do this, I could replace 0 with y, graph it, and the x-intercepts are my solutions. So it's kind of like a weird little trick. That's the easy part. The hard part was knowing how to graph it. So that's why I spent the majority of this video explaining that. And we'll catch this concept when we're doing our party quest in just a moment. Thanks for watching, internet friends. It's been a pleasure.
That looked